Yeah, good evening. Let me first quickly complete up the theory part of electrochemistry. This is the last part which we have to finish. And as we're done with it, then we'll start solving the questions. Okay. See, what has been noticed when you take electrolyte into the solution? So, we can have two types of electrolytes. One, weak electrolyte or strong electrolyte. Weak electrolyte could be something like weak acids, acetic acid, or any organic acids, or in generally uh, HF or something. These are all the weak electrolytes. Strong electrolytes would be something like salts, KCl, NaCl, or NaOH. Okay. In fact, HCl is also a strong acid for that matter. Yeah. Okay. So, in case if you try to check out what happens to this molar conductance, okay, for weak acid, for weak electrolytes and strong electrolytes, experimentally, it has been observed that when it comes to strong electrolyte at different concentration values like this, we've been able to figure out different lambda m values. That means as the concentration was increasing, in fact, the other day we learned that when it comes to lambda m, which is equal to kappa into 1000 by C in Simon centimeter square mole inverse. This is the formula we learned. We learned that as the concentration decreases, K value decreases, but lambda m value increases. It is because the concentration decrement is way higher compared to that of the decrement of specific conductance. Hence, lambda m always increases. This is what we learned. Now, that's what happens both with weak electrolytes as well as strong electrolytes. So, if it comes to strong electrolytes, as the concentration is increasing, you will see more of decrement in terms of molar conductance, right? And experimentally, it has been found that we can actually make a linear relation between lambda m versus root c. Instead of c, now we are plotting that with root c. Got it? But when it comes to weak electrolytes, at higher concentration, you will hardly see any change. Of course, it's not increasing. That's not how it is. But I meant to say it will start, decreasing like this all the time. Got it? So this is for weak electrolytes. But as the concentration decreases, the lambda m value drastically increases. Okay. And you notice that as the concentration becomes very close to zero, the lambda m value shoots up. Got it? So what we can conclude from this graph is that on dilution, increase in lambda m is more for weak electrolyte than in strong electrolytes. Second, we can calculate the lambda m or lambda m naught or lambda m infinity. What does this mean? Lambda m naught means zero concentration, or lambda m infinity means infinite. Uh, when you have the highest value, lambda m infinity, as in when you have the infinite dilution or the highest value. So both of them meant the same thing, but just the reading is different. Zero is with respect to zero concentration, or infinity is with respect to infinite dilution. Then we will be able to extrapolate the strong electrolyte, but for weak electrolyte, it is difficult to determine the graph. What does that mean? For example, if I get these 3 points only during experiments, I can extrapolate them and try to figure out what is lambda m infinity. But for weak electrolytes, we can't extrapolate like this because it will keep on going up without touching the y-axis. Therefore, it is difficult to find out what is lambda m infinity for a weak acid using the graph. But for strong acid, we can figure out this one. Okay. So these are the points we learn. So from here, you will see lambda m how it is related with root C. Okay, this is called as, you know, Onsager Debye equation. Got it? Debye-Huckel's equation. What does this mean? Is it is a linear dependency of molar conductance with respect to root C, wherein you will get this as lambda m naught has the y-intercept and the slope will be negative with a minus a value. Okay, sometimes this will be given as b also, so it is just a constant value. So which means in some equations it is given as lambda m naught minus b root c. Right. So it is basically a constant here. B is a constant here, or A is a constant here. So this value of A mainly depends upon the nature of the solvent. What is the temperature of the electrolytic solution which is present in the solvent? Okay. Now notice all the electrolytes of a particular type have same value of A. Okay. For example, if you take MgSO4, it has plus 2 and minus 2. If the charge overall is higher, plus into minus charge, if it is highest value, then it carries to have a higher A value. If you notice CaCl2, calcium has plus 2, chlorine has minus 1. NaCl, Na plus has plus 1, chlorine has minus 1. So this is how the value of A decreases. Got it? And if you have 1 is to 1 ratio of the charges, the A value almost remains the same. Got it? Now, from Oswald's dilution law, if you recall, that is, for example, if you have something like Ha as a weak acid and I have H plus and A minus, initial concentration is C naught, and then we have C naught multiplied by 1 minus alpha, and this will be C naught alpha and C naught alpha. In that case, Ka will be equal to under root of, okay, K will be equal to C naught alpha square by 1 minus alpha. And if I ignore this alpha, alpha will be under root of Ka by C naught. Okay. So we know that as the concentration decreases, alpha value will increase. This is what we call it as Oswald's dilution law. And at infinite dilution, alpha will become 1. Okay. So that's why it gives the maximum value. Got it? Nice. Check out. Now, let's understand what is Kohlrausch law. According to Kohlrausch law, if you are operating at infinite dilutions, got it? So all the weak or strong electrolytes will be 100% ionized, isn't it? Because a weak electrolyte will be 100% ionized. That means alpha value will become equal to 1 when you have it at infinite dilution. That means highest amount of dilution. Then 100% ionization is observed. In that case, whether it is a weak or a strong, both of these ions at an infinite dilution will start behaving like an independent ions, which means they will have hardly any affinity. They will be away from each other in the solution. Like for example, if I take NaCl, lambda of NaCl implies that lambda m of Na plus and lambda m of Cl minus. Okay, that means lambda m infinity can always be written as the sum of the molar conductance of their respective ions. Okay, why we can write this? Because it is a strong electrolyte and at infinite dilution, correct, they will be acting independently. So therefore total conductance will be Na plus and Cl minus conductance. Likewise, if I write it for KCl, it will be the same. So now My point is, if you want to get, let's say, if you are trying to figure out the value like this, lambda m of Na plus minus lambda m of KCl, right? So in that case, it will be x minus y, and x minus y will be equal to, you can see now this Cl value can be cancelled off. Why? Because it will be the same value whether you are getting it for NaCl or whether you are getting this value from K plus. So every ion will have a specific value of lambda m infinity. That means at infinite dilution, they will have a specific value as they are behaving completely independent. Okay, just a second. So similarly, if you see lambda m Na2CO3, if that is W, K2CO3 is Z, then subtraction of these two will be 2 times of lambda m infinity minus 2 times of lambda m of K plus. And that will be 2 times of lambda m of Na plus minus lambda m of K plus. Now here you are getting this as W minus Z, and above you are getting it as X minus Y. So this relation is W minus Z is equal to 2 times of X minus Y. So therefore, everybody at infinite dilution, every individual ion has its own value, and that is same whether it is derived from X salt or a Y salt or a Z salt. Okay. So this law states that the limiting molar conductivity, which is lambda m infinity or lambda m naught, of an electrolyte, weak or strong, can be represented as sum of individual contributions of anions and cations of the electrolyte. And if at all we have AX and BY this way, then you know that it can be written as X times of A plus Y times of B minus X. And lambda m infinity will be equal to X times of lambda m infinity of A plus Y and lambda m infinity of B minus X. And this we have done it as a question already, that when it comes to equivalent lambda m infinity, then lambda me of particular ion plus lambda me of the other anion will be the sum of that. There will not be any coefficient multiplications here. So that is one important thing to understand. Got it? Now let's notice how this degree of dissociation, dissociation constant for weak electrolyte, how they are related with each other. Okay. So now let's say we have, let's assume that I have a solution which is having a acid HAC. Okay, something like acetic acid. Correct. So for an HAC, let's say the concentration is C1. This has concentration C1. Correct. And you know that HAC, HAC here, this concentration, initially it is 0 molar. Correct. At infinity, I mean, when the concentration is, um, yeah, when it is at almost 0 molar, correct? And then alpha value will be equal to 1. Sorry, initially it is not 0 molar, it is some C molar. It is some C molar, C1 molar. And as the time passes and it becomes T is equal to infinity, that will become 0 molar. And when it becomes 0 molar, I can say alpha value will be tending to 1. Correct? And we know that lambda m infinity for HAC will be equal to lambda m infinity of H plus lambda m infinity of AC minus. This is what you know. As per Kohlrausch law, we can write that. So I can say that lambda m infinity of HAC is basically representing the alpha value as 1. When alpha value is 1, this will be the molar conductance. Okay. So if the lambda m value is 1, then what will be the value of alpha? Then that will be equal to 1 by, lambda m infinity of HAC, isn't it? This is for 1 unit change of alpha. Correct. So what if you have lambda m of HAC? That means when you have some conductance of lambda m, then alpha value will be equal to lambda m of HAC divided by lambda m infinity of HAC. This is what it is related with. Correct. So alpha is equal to lambda m by lambda m infinity. So check this out. Ka is equal to, correct? Ka is equal to C1 alpha square by 1 minus alpha. So which is equal to Ka is equal to C1 into alpha now can be written as lambda m by lambda m infinity of that weak electrolyte minus 1 minus square here lambda m by lambda m infinity. So this is the value of Ka. Everybody clear? So in case if uh, alpha value is less than 0.05 in our calculations, then we can ignore the uh, term in a denominator term, and Ka value will become C1 lambda m by lambda m infinity whole square. Correct. So this is how we can relate it. Okay. So I hope this part is clear, everybody, how it is to be related with the alpha value, what is K value, how it is related with lambda m and lambda m infinity. Okay, please go through it once. If you have any doubt, please let me know. The second point is about determination of ionic product of water. Ionic product of water, which is IP, or we write it as KW. Okay, so let's solve that. KW, or simply I can write it as ionic product, is concentration of H plus into OH minus for water. So if I have to write K of water, that is, this is specific conductance of water. Then because specific conductance is additive, it will be K of H plus K of OH minus. And by formula, if you know this, that lambda m of H plus, for example, will be equal to kappa of H plus into 1000 divided by concentration of H plus. So I can write it as H plus concentration. Similarly, I can write lambda m of OH minus will be equal to K of OH minus into 1000 divided by OH minus concentration. Correct? So you can see these two can be related as, equation 1 and equation 2. These two can be related here. Okay. Now, if I substitute this back with respect to K plus and KOH minus, I should be able to get the K of water here. So therefore, K of water or kappa of water is equal to lambda m of H plus into H plus concentration divided by 1000 plus lambda m of OH minus into OH minus divided by 1000. This is the value which you will get. Okay. Now, we know that ionic product of water Kw is equal to H plus concentration into OH minus concentration. And for pure water, we know that H plus concentration is also equal to OH minus concentration. Right? So if I take that concentration term equal, so if I take H plus concentration divided by 1000 as equals, then I'll get this as lambda m of H plus lambda m of OH minus, that into K of kappa of water. So therefore, kappa of water is equal to under root of Kw divided by 1000 into lambda m of H plus lambda m of OH minus. So this is the way you can figure out molar conductance of water. as long as you know K of water and lambda M plus and lambda M naught value if you can consider that. Okay. But if you want to figure out Kw, because that is our whole purpose, how to figure out Kw. Kw will be equal to kappa into 1000 divided by lambda M of H plus lambda M of OH minus whole raised to power of half. So that will be the value of Kw. Okay. Experimentally, students, this is how you figure out what is the value of Kw, ionic product of water at different temperatures. If you find out, what do? We calculate the specific conductance of water. Okay. That is also experimentally done. And these two are experimental values anyway. Add those two values, take the root of it, you'll get K of W. Got it? So this is how you can figure it out. Okay. How much it will be. So one second. See, next one, the same logic is to be applied even if you have a solubility product. Okay. So if you want to figure out solubility product and case P given, for example, if it comes to something like AgCl, I'll take the example of AgCl. AgCl is in equilibrium with Ag plus aqueous plus Cl minus aqueous, and the equilibrium constant is Kw. In that case, I can, sorry, Ksp. Equilibrium constant is called as Ksp. So we know that Ksp is equal to Ag plus concentration into Cl minus concentration, which is also solubility square. So S is equal to under root of Ksp. So now our objective is to figure out S. From S, we can actually get Ksp experimentally. So how is these two related? So now notice, can I write this same equation once again? Please notice this carefully. That actually AgCl solid is going to get dissolved first. And how does it get dissolved? AgCl aqueous, correct? And a small amount of dissolution will happen. I mean, this is a complete solid substance that will get dissolved into AgCl. And it is this AgCl dissolved form which will ionize completely into Ag plus and Cl minus aqueous. So, of course, anything which is in a solid substance is not something which is going to be useful for conductivity. And it is the ions which are useful, right? So, suppose if the concentration of this AgCl is S, then this entire S will dissociate into getting this as S into S, which means if I want to calculate what is the molar conductance of AgCl aqueous, then that is molar conductance of Ag plus and Cl minus. Is that clear? So therefore, from there I can get what is the value of solubility also. Therefore, so I can write lambda m of AgCl solid, that will be kappa of AgCl solid, correct, into 1000 divided by concentration. Concentration of AgCl which is dissolved in water, how much it is getting? S. So from there we can calculate S. So S is equal to kappa of AgCl into 1000 divided by lambda m of AgCl. Okay. Hence, if you know that, from here we can figure out, correct, what is the value of Ksp. So Ksp is equal to S square, which is equal to kappa into 1000 by lambda m ka whole square. So this is how you can figure out or make a relation between Ksp with molar conductance as well as specific conductance. Everybody clear on this point as well? Please check. So we don't have to worry when weak electrolytes are given. So this is how we can calculate it. If any sparingly soluble salt is given, again, this is how we can calculate. Right. Now notice this question. The equivalent conductance of lambda E of NaCl, lambda E of HCl, lambda E of this acid salt and this acid. You need to find a relation between these three, four. This is unknown because it is weak. For weak value, it is difficult to calculate, right? That's what we learned in the graph. That for weak, it is very difficult because it will keep on going. We can't extrapolate it. But for strong, if you know 2 points, we can extrapolate it and calculate the maximum lambda value. Okay. So you can see for a weak acid, zero point 0.1 molar of this lambda E of this weak acid is given. Then what is the value of alpha and what is the value of Ka we need to figure out. So please check this out. Since we know the lambda E value, right? So if you notice, how do I get this value from these three? See, I need to eliminate Na plus and Na plus. So which means I will take this compound and subtract NaCl. So Na plus will get subtracted anyway. Cl minus I have to subtract means I have to add this one now. So therefore, I can say lambda E infinity of Cl CH2COOH will be equal to lambda E infinity of Cl CH2COO minus plus lambda E infinity of H plus. Now to get these two values, what should I do? I can take this strong electrolyte data and add like this. So lambda E infinity of Cl CH2, this is CH2, CH2 COO COONA, that plus lambda E infinity of HCl minus lambda E infinity of NaCl. So Na plus and Cl minus uh, both will get cancelled out of this equation. So therefore, this will be 89.8 plus 426 minus 127. Correct. So that will give you lambda E infinity value. Correct. So this value I'm getting it as 388. Correct. 388. Acha, 0.8 also. 388.8. So this will be ohm inverse, correct, and centimeter square and mole inverse, right? So this is the sorry, not mole, equivalent inverse, because we are talking about equivalent conductance. Now see, the question is, if zero point 0.1 molar of this one is given, so concentration is also given. So from there, lambda m infinity value, okay. So how do we calculate the alpha value here? Alpha value is equal to lambda E of Cl CH2COOH, that divided by lambda E infinity of Cl CH2COOH. This is how we can calculate alpha. Okay. And how much is the alpha value of E given? Alpha value of E at this concentration is already given, which is 38.8. So 38.8 divided by 388.8, that makes it 0.1. So this is the alpha value, which is 0.1. Okay. So if this is alpha value, then what about the K equilibrium value? So K equilibrium value, which is equal to C alpha square by 1 minus alpha square. Sorry, 1 minus alpha will be equal to 0.1 into 0.1 square by 1 minus 0.1. Okay. So 10 raised to power of minus 3 by 0.9. Okay. So if you multiply that, I'll get this as 1.1 into 10 raised to power of minus 3. So this will be the equilibrium constant value. Okay. And since it is an acid, I can call it as Ka. So Ka of ClCH2COOH is 1.1 into 10 raised to power of minus 3. So that's how we can calculate Ka. That's how we can calculate alpha. We can calculate lambda E infinity. All of this information can be calculated. Please check this out, everybody. It's an easy one. I hope you guys understood how to solve it. Let's learn this. Theoretically, this is the last topic which we need to know. conductometric titrations. Basically, the independent values of lambda m infinity for various cations and anions is this list. So if you may have noticed, the H plus value, lambda m infinity H plus value is very high as compared to that of other cations. Okay. NH4 plus is exception because NH4 plus is a very bulky molecule which also has an H plus in it. But other than that, you take a general cation values, they are very high values, right? I mean, they are all, sorry, smaller values compared to H plus values. Likewise, if you compare OH minus value, this OH minus will have relatively again higher value compared to that of other anions. Okay. Of course, FeCN6 4 minus has very high value because of the high charge that it carries. That is an exceptional case. But otherwise, if you compare OH minus with any other ions involved, generally OH minus is a higher value. Likewise, in cations, H plus is a higher value. Correct? So now can I say one thing? In a solution, if H plus concentration increases, then definitely molar conductance should increase. Or in a solution, if OH minus concentration increases, then also molar conductance should increase. Or vice versa. If H plus is decreasing or OH minus is decreasing, then we can expect lambda m also should decrease. Hence, in generally, when you have lambda m infinity value for a divalent cation, it is usually more greater than that of monovalent. You can see that Mg2 plus will have higher value than K plus, monovalent versus divalent. Since H2O is a medium, lambda m of H plus and OH minus is very large with respect to other monovalent atoms. Because OH minus and H plus will keep moving very fast or extremely swiftly between the electrodes, correct? Hence, they carry high amount of molar conductance values. So, in generally, on increasing the charge on ion, the value of the lambda m always keeps increasing. That means it will become more and more plus or more and more minus. The lambda m values will always keeps increasing. Okay, this is the idea we should have, everyone. Okay. Now, what is the principle behind this conductometric titrations, everybody? Here, the principle is it is based on the fact that the titrations, one of the ion is replaced by the other, isn't it? For example, if you take HCl and NaOH titration, as you keep on adding NaOH, the H plus is eventually replaced with Na plus, isn't it? Because you are getting to we are getting a formation of a salt. So H plus is being removed, Na plus has been replaced. Correct? That is exactly what we are trying to understand here. So when it comes to any type of acid-base reactions, there is always a replacement of ions. And it is the replacement of ions which will result in either increase or decrease in the molar conductance. Right? So now notice this one. First thing we learn is about strong acid and strong base titration. How does it vary? Okay. So how do we need to understand graphically that what might be happening here? See, if you take a extremely small sized burette like this is called a micro burette, and that is being added to a flask of HCl like this. Okay. And in the flask of HCl, the electrodes are connected like this to a source here, correct? And from here also they are connected like this. This is how they are connected. Okay. And this is usually an AC source. Okay. Alternating current source. And now notice what might be the reaction happening here. So because this is an HCl here, as you start titrating with NaOH in the microburette, imagine I have NaOH, and as you titrate with NaOH towards HCl, the H plus ion is being replaced by Na plus. Okay. So of course the overall reaction what is happening is like this: HCl aqueous plus NaOH aqueous is treating with each other to form NaCl aqueous plus H2O liquid. So this is what has been happening. Clear? Now what we can say that as the because initially we have only HCl, and as the titration is proceeding drop by drop as we add NaOH to it, H plus has been replaced by Na plus. Correct? So over the period of time, all the H plus will be replaced by Na plus only. So what should happen to the molar conductance? It should decrease. So that's why if you identify the graphical idea about how the lambda m value in the solution changes with respect to volume of the base that is being added, volume of NaOH that is being added. So you will notice that it will be initially decreasing like this. It will be initially decreasing like this, correct? And after a point of time here, it will reach to a certain value here. And from there, afterwards, what would happen? You see that also, that after a point of time, again, you will see a small increment towards this side like this. This is how the increment takes place. So now you notice this one. This point is what we call it as the equivalence point, where the titration is being completed. And in this zone, H plus is being replaced by Na plus. And what about in this zone? In this zone, now what's happening? Because after the titration is done, okay, one minute. Look, then Na plus is been, I'll come in. Okay, then here, after the equivalence point has reached, again, if you keep doing further titration, now the Na plus ion concentration is also increasing. OH minus concentration is also increasing. Now, because of the increase in the number of ions as well as the OH minus concentration, again the conductance will start increasing. Of course, it is extremely difficult to figure out the exact equivalence point. That's why we need to extrapolate the experimental values. So that is, these are all the experimental values. So you find one value here, one value here, maybe one value here, and one value here. And afterwards, after the titration is complete, you will find out the values like this. Now, basically, you draw one line like this, you draw one line like this. That intersection value is what is equivalence point. Everybody, I hope you guys understood how the titration works for HCl and NaOH. It's very simple one. So I don't think there is much to discuss, but still, if you have anything to add or anything you want to discuss, please let me know. Here, I'll just put that in the words so that it's clear for your understanding that what is exactly happening here. Correct? Before adding, before adding NaOH, HCl shows high molar conductance, high molar conductance due to highly mobile, highly mobile H plus ions, due to highly mobile H plus ions. Okay, clear? Then as titration proceeds, as titration proceeds, H plus is replaced by slow moving Na plus ions. Hence, molar conductance of the solution decreases. That's what we noticed. Clear? The intersection curve of two lines the intersection point of two experimental experimental lines is the equivalence point. That is the equivalence point. Got it? So I hope all of you understood how the graph works there, right? And next, notice how the weak acid and strong base graph works now. Now let's focus on this part. What do you mean by weak acid and strong base? This time, in the solution, while titrating, correct? While titrating, the solution what we have here is a weak acid. Let's say HAC. This is the weak acid. And from top of it, we are adding NaOH. And electrodes are here to measure how much amount of molar conductance it is happening. Correct. So now how does this proceed? See, this is very interesting. You can learn it through number of ions and so. So please check it out. Initially, before adding NaOH, imagine we have 100 particles or 100 particles of ACHAC ACOH acid. Let's say I'll take acetic acid only. Why to confuse with other one? This is easier to understand. Acetic acid. 100 particles of acetic acid are present. Imagine initially. And initially, out of this 100 particles here, before adding only due to its weak dissociation, let's say there are two particles and two particles already dissociated, which means currently I have 98 particles of acid, two particles of ionized and two particles of ionized acid. Okay, this is the current situation, everybody. Before adding NaOH, and this at this point, whatever be the measurement you can make, that is the lambda m, right? Value of ACOH initially. Initially, what will be the value that you will get? Okay. Now, what you're doing, as the NaOH is getting added, the first thing what would happen is that OH minus will first consume the H plus which is already present and convert that into H2O. Correct? So here also, of course, you are adding Na plus and OH minus. Correct? So how many you are adding? Let's say you added 2 drops of it and there are 2 drops of or 2 ions of H plus initially. So these two will get consumed. So what is left here will be Na plus of 2 moles or 2 particles, and then you will have H2 of 2 particles, and water is of no use to us. It is not an ion. So which means initially 2 moles of this H plus is been consumed by 2 moles of NaOH, and there will be a decrement in the lambda value. So I can say that here lambda m value decreases. Okay. But notice, of course, you might argue with me, sir, ये H plus जा रहा है, तो equilibrium will shift in the forward direction. Of course, that's what will happen, but it will take some time. That equilibrium to attain, it will take some time. So at the first instance, this H plus will be immediately consumed. Okay. And now, if you further add NaOH, assume that equilibrium is taking time, but you're not stopping the titration. In that case, the second mole of Na plus and OH minus, if you add, then directly CH3COOH will get or ACOH will get reacted with this one. So ACOH will react and you'll get, suppose if I added 2 moles here, 2 moles here, and this was 98 particles. So now out of these 2 particles, OH minus will be lost. Now this will become 96. And here we will get this as ACO minus, which will be of 2 particles, and H2O will be there of 2 particles. and that's it. This is what you will get. So eventually you will have, after the reaction, you will have two particles of NaOH, two particles of ACO minus. Okay, correct. But initially, how much it was? I mean, just after this titration, what was there in the solution was 98 particles of ACOH. But from that, that is an undissociated or unionized acid. But now, on adding NaOH, you are getting two ionized ions, I mean, two ions of ACO minus and two ions of Na plus. So naturally, over the period of time of titration, the number of ions are increasing. Number of ions present, ions present is increasing. And as the number of ions increases, everybody, then lambda m value will start increasing. So that's how the titration works here. Of course, this increment is not very drastic because it is not coming from a very strong acid. Hence, now if you place the graph, how now if you notice the graph, how does it work? So you can see initially for a small bit of time, the conductance will start decreasing, correct? And from there, as you can see, as it starts growing here, the conductance will start increasing. So from here, conductance will start increasing like this. And from here, at some point, it reaches the neutralization part. And thereafter, it further increases because once the neutralization is been done, at this area, we are having ACO minus ion concentration and Na plus ion concentration increase. That's why it is an increment. At this point, you have Na plus and OH minus ion concentration increasing after the neutralization point. Hence, again, conductance increases. So this short decrement in the acidic acid or any weak acid is because H plus is getting replaced by Na plus momentarily. In that moment, it is getting replaced. This is a graph you should notice for weak acid and strong base. Got it? Let's see the next titration. Now, this titration is about weak acid, strong acid mix that is being titrated with NaOH. So, in this titration, let me take this image. So, here I have mixture. So, it is a mixture of HCl plus ACOH. And then you are making a titration. Now, what would happen? As long as HCl is present, the first titration will be about this only. That it will become NaCl and H2O when it is about, okay, up to completion of, 1 second, up to HCl is finished. And once HCl is completed, right, then ACOH will start. ACOH will start titrating. And then you will have ACO minus plus Na plus H2O. So both of them individually, we have seen how the graph works. So now I'm writing the same graph for together, both of them. So initially we learned that as the HCl decreases, the conductance will decrease. So that is fine. So after this, we will get a point where this is like the first equivalence point where HCl is finished. Thereafter, of course, when HCl is finished, that will also consume any amount of H plus that is contributed from ACOH, right? So this smaller part will not be visible anymore. So this smaller part of decrement of lambda m is not visible anymore. Hence, the second part is always about the next titration, which is moving like this. Okay, this is where the acetic acid is uh, titrated with NaOH. This is the second equivalence point. And from there, it will further increase as usual because NaOH has been increased. So same thing here, H plus H plus is been replaced by Na plus. Here ACO minus and Na plus concentration, both of them are increasing. That's the reason why lambda m is increasing. Here Na plus and OH minus concentration, both of them are increasing. That's the reason why lambda m is increasing. So it is like just a mix of these two, this one as well as this graph. If you mix both of them, you will get this graph. Okay. So I guess the third part is clear how it is working. Got it? Next, check out weak acid, weak base. Okay. No. I didn't write weak acid, strong base first. Strong acid, weak base. Weak acid, weak base. Yeah. I'll do one thing. I'll write down here only. Okay. Like a special case. So the next case we'll see is about weak. This is about weak acid, strong base. Weak acid, strong base. Okay. Sorry. Weak acid, strong base we have done, right? Sorry. Yeah. So let's see. Next iteration is about how the PPT formation is observed. What if you have any PPT formation? How is it observed? Correct? That is, in case if you have AgNO3, the same thing, I'll put this as a diagram here, just for understanding sake. So imagine in this, we have AgNO3 here, AgNO3 initially, and that is being titrated with KCl. That is being titrated with KCl. So on doing so, the reaction which you will get is like this: AgNO3 aqueous will be treated with KCl aqueous, and that will form AgCl solid plus KNO3 aqueous. Clear? Now notice this one. Here we go with one assumption, everybody. That is, lambda m infinity of Ag plus is almost same as lambda m infinity of K plus. Lambda m infinity of Ag plus is almost same as the lambda m infinity of K plus. Got it? So which means initially you can see Ag plus is basically replaced by K plus. And since Ag plus is simply replaced by K plus, do you see much of a change in the lambda m value? Not so much. So we will see lambda m versus volume of KCl added. In that case, initially you will hardly notice any change in the molar conductance. Okay. Then as it reaches to the neutralization point, thereafter it increases. Why is it increasing? Here see A plus is decreasing and K plus is increasing. Correct? And they are compensating. But here you will see K plus is increasing. NO3 minus concentration, sorry, Cl minus concentration is also increasing. Because the number of ions are increasing, lambda m value is increasing in this case. So any PPT based cases, this is how you have to check it out. Now, this is one case. What if I took lambda m infinity of Ag plus, correct, is slightly greater than lambda m of K plus. If this value is slightly greater, correct? In that case, how does the graph work? Please check it out. So in this case, what would happen? Initially, Ag plus concentration is getting decreased and K plus has been replacing that. So definitely there will be a slight decrement in the concentration initially. So from here, this is how it decreases. It will go and touch here like this. Got it? Just a minute. So lambda m value will be going this way. Okay. Now assume the other case, the last case here, correct? That is lambda m, if lambda m of ag plus is less than lambda m of k plus, correct? So in that case, graph will be slightly like this, where initially, because k plus is increasing, the molar conductance should slightly increase as well. So this is how the increment value will be like this. So here K plus value is increasing, Ag plus concentration is decreasing. So this is how the graph will go. Okay. As per NCRT, only this graph is given, correct? But in JE, these two have been also asked, like what if the concentration, what if the molar conductance are slightly different? Then how does the graph vary? So guys, the PPT case is clear how it goes, if depending upon lambda values, how it has to be changed. Okay. Done. Next. Notice weak acid and weak base. In case if you have a weak acid and a weak base, what will happen? Okay. So for the case of weak acid and weak base, let me show you which of them are weak acid and weak base. Like CH3COOH plus NH4OH. Got it? So if you have a weak acid, weak base, right? So then uh, consider one of them is in the burette here. So we can take the same graph here. I can say, let's say NH4OH is being added in the burette, NH4OH, and in the solution we have acetic acid, CH3COOH. Now, as you add these two, so what is the reaction that will take place? Initially, CH3COOH was mildly ionized into CH3CO minus and H plus. So as soon as you add NH4OH, initially it will consume this small amount of H plus and convert into NH4 plus plus H2O. NH4 plus plus H2O. Correct? So especially in this case, you can see the H plus is being replaced by NH4 plus. So actually conductance should increase, right? Because NH4 plus will have the highest amount of conductance here. So you will not see any decrement in the conductance here. Then as the titration keeps further happening, then we expect that NH4OH plus CH3COOH is getting titrated, and that will form CH3CO minus and NH4 plus. So this is how it will go. So initially again the titration value will increase here. So graphically, if at all I show it, so lambda m values right from the start, it is going to be increasing. Okay, sorry, the lambda m value starts increasing, correct? It will reach to a tight end point here, and from there slowly you will see hardly much of a difference is observed thereafter, because you will see NH4OH is present after that, and NH4OH is unionized, correct? Because it is unionized, it will be almost constant. So NH4OH value is increasing, that is unionized, so it is hardly going to make any difference here. NH4 plus concentration is increasing, as well as CH3CO minus concentration is also increasing. That's why there is a raise in the lambda m value. This is about weak acid and weak base case. Everyone understood? Okay. Strong acid and weak base is the similar case here. If you have a strong acid and a weak base, see, strong acid and weak base is like HCl titrating with NH4OH. Got it? So suppose if we have strong acid here, which is HCl, and we have NH4OH. Here the graph have to be analyzed in two different ways, everybody. The first way is when NH4OH is in the burette. In that case, definitely I'm sure you can relate it without any note here. You should be able to relate that lambda m versus volume of NH4OH added, because now it is about volume of the NH4OH added. So if it comes to volume of NH4OH added, then what will happen? See, initially H plus concentration will decrease. Initially H plus concentration will decrease. Okay. And it reaches to almost neutralization point. Thereafter, you'll hardly see any increment here because this is a weak acid. This is a weak base. So here we will see NH4OH concentration is increasing, which is not going to increase a lot of ions here. But here H plus concentration is decreasing, which is replaced by NH4 plus. Okay. Now here is the interesting part. Of course, NH4 plus is usually, we assume that NH4 plus will have a higher value, correct, compared to that of H plus. But while comparing in the solution, I would suggest you always take this as a graph, because here NH4 plus will become an exception, but otherwise, if at all there is H plus concentration decrement, that is always going to decrease the molar conductance. Okay. Especially in this case, guys, don't just simply go with the value of NH4 plus and H plus. Think only in terms of H plus. If H plus is decreasing, always there is a decrement. Now, second case is this scenario, if at all I change, if this scenario I change that instead of NH4 here, I'm saying HCl is here and NH4OH is here. Okay. In such case, how does the graph vary? See, this time, check. So initially we had NH4OH. This would be exactly the similar case what we have done for weak acid and strong base. So initially there will be a small decrement here, and thereafter it will start increasing and it will reach to a neutralization point. From there it will start raising up. Okay, correct. This is the neutralization point. Okay, and at this point initially H plus concentration decreases. Here NH4 plus concentration is increasing, as well as Cl minus concentration is increasing. And at this point, H plus concentration is increasing. Done. So this is how the strong acid weak base functioning would be observed. Okay. So guys, please do check. If you have any doubt, you can immediately ask me. 1 second. I'll put this above only so that we can refer it easily. Yeah, please check all of these graphs at once in one glance and let me know if you have any doubt. Right, now let's see this question. The resistance of zero point 0.1 normal KCl solution is given. Calculate lambda m, lambda e of the solution if the cell are 4 centimeter apart of each other, having an area of 8 centimeter square dipped into the electrolyte. Okay. So first you need to figure out the resistance. I mean, write the formula for resistance. So that is equal to rho into L by A, correct? And if I write that in terms of kappa, which is 1 by rho, is equal to L by A into 1 by R, correct? L is the length, which is 4. A is the area, which is 8. Resistance is 1 by 250. So that is equal to 1 by 500 ohm inverse and centimeter inverse. Okay. And then we know that lambda m is equal to kappa into 1000 divided by concentration. Okay, in molarity. Because KCl is given in normality, molarity and normality of KCl is same as valency factor is 1. Therefore, I can write this as 1 by 500 into 1000 upon concentration. Concentration is zero point 0.1 molar. So that makes it 2 divided by zero point 0.1, which is 20. So 20 ohm inverse centimeter square and mole inverse, or Simon centimeter square and mole inverse. So that is the units of it. So this is about lambda m. Lambda m and lambda e will be same for this case. So that is also 20 Simon centimeter square and equivalent inverse. Okay. So I guess this part is clear, everybody. So it's a simple question. Okay. I'm not sure what was struggling. So please check it out. Any doubt here? And everyone? All right. So now check out this case here. Calculate solubility and solubility product, that is S and KSP, of cobalt iron cyanide in H2O. Here cobalt is +2 oxidation state, just to remind you. The conductivity of saturated solution of a complex is given the molar mass of cobalt +2, FeCN46. These are the values which are given. So use that values and try to figure out what will be the solubility and solubility product of this particular salt which is solid. Okay, so try it for a minute, then I'll discuss. See this case. So basically, if you have resistance 50 and 100, but you are taking in the same molar, same conductivity cell. Now, what would happen is, since you are taking the same solution, both are of equal volume, so this value, I mean the resistance value here, correct? Um, yeah, I mean, let me put it like this, okay? K of the mixture should have been equal to K of A plus K of B, isn't it? This is what it should have been, okay? So now what would happen here is, when you have uh, concentrations here, you know that cell constant, which I can write it as G star, right? Which is equal to L by A, and kappa is equal to G star by R. Let's use this part. Because you are using in the same dimensions of a cell, I can say K of mixture should be equal to Ka plus Kb. But here is the interesting part. When I say Ka here, this K plus Kb is basically original I'll write it as Ka dash here. And this will be equal to original Ka by 2. Why by 2? Because the minute you increase the volume or double the volume, the number of ions between the electrode, between the plates, will also become half of it. So therefore, conductance will also become half of it. This is what will happen. So therefore, if you have original conductance, you can see Ka is, G star, which is constant, divided by R of A into 2, plus this will be G star of R of B into 2. So that is equal to G star is a constant value here, correct? That into 1 by 2R. R was 50, so it will become 100, plus 1 by 100, so that will become 200, correct? And overall G of mixture is G star by resistance of the mixture, correct? So now G star will get cancelled. So 1 by resistance of the mixture should be equal to 1 by 100 plus 1 by 200. So that is equal to 300 by 200. Correct? Sorry, 3, not 2, 200. Sorry, 3 by 200. Okay. So now I can write R of mixture is equal to 200 by 3. So which is equal to 66.6 ohms. So I suppose this part is clear, everyone. Please check. Any doubt?